Good day, everyone. I am Jedd Causapin from BS GeolEng 3202, and today I'll be presenting the study titled Ambient Noise Surface Wave Imaging in a Hardrock Environment Implications for Mineral Exploration. This research focuses on the use of passive seismic methods to map subsurface features in complex hard rock environments, offering cost-effective alternative to traditional seismic approaches. To understand why this method is significant, now let's begin by looking at the challenges of traditional seismic exploration and how ANSI presents a promising solution. Traditional seismic exploration often faces limitations in hard rock settings due to low acoustic impedance, contrast, metamorphism, and structural complexity. This study explores an alternative method, which is the ambient noise seismic interferometry, or ANSI. Unlike conventional seismic, ANSI does not rely on artificial sources. Instead, it uses natural and man-made background vibrations such as those from traffic or industrial activity to retrieve surface waves. The surface waves, particularly the relay waves, are then analyzed to image subsurface structures like faults and lithological boundaries. With this method in mind, let's move on to the specific objectives the researchers aimed to accomplish through the study. The study was guided by four main objectives. First is to evaluate the use of ANSI in a hard rock mineral exploration context. The second is to extract shear wave velocity profiles from passive seismic data. Third one is to validate those profiles using active source seismic data, and the fourth one is to assess whether these methods can enhance geological interpretation and support mineral targeting. Together, this aims contributes to improving subsurface imaging in environments where traditional seismic methods are often costly or ineffective. To see how these objectives were applied in the field, let's take a look at the study area where the data was collected or were collected. The fieldwork was carried out in Blotberge, located in the Bergslagen or province of central Sweden. So this region is historically significant for mining and is known for hosting iron oxide apatite and rare earth element mineralization. The local geology consists of Paleoproterozoic metavolcanic and granitic rocks overprinted by deformation and mineralization. The figure shown includes four panels, which is the topography and elevation data, bedrock geology, magnetic anomaly distribution, and soil types. The seismic profile line runs southeast across varied geological formations and aligns with known mineralized trends. So, with the site context established, let's examine how the seismic data were acquired. So, in the study, a 2.4 kilometer linear array was developed with 492 vertical components. Component MEMS accelerometers spaced 5 meters apart. So passive seismic data were recorded over 4 nights, capturing ambient vibrations from nearby roads and railways. So in parallel, active source data were collected using a 77 kilonewton seismic vibrator that generated frequency sweeps ranging from 2 to 200 hertz. This setup enabled the collection of a broad frequency spectrum and low frequencies from passive data for deep imaging, and also high frequencies from active data for detailed imaging of the upper 75 meters. Combined, the datasets provided a continuous broadband velocity model ideal for structural interpretation in a hard rock environment. So now that we understand the data collection process, let's walk through the workflow used to analyze the data. So the methodology followed a structured workflow. First is the active source data were used to develop a reference 1D velocity model. Next is the passive data were processed using cross correlation between receiver pairs to generate virtual shot gathers. Next is the surface wave analysis was then performed using the MHW technique to extract dispersion curves. Then these curves were inverted to produce 1D shear wave velocity profiles. Finally, the results from passive and active data were merged to create a detailed 2D velocity model of the subsurface. With this overview in place, let's look more closely at the modeling process using the active source data. So, using the active source data, a velocity gradient was estimated based on first arrival travel times. Synthetic shot gather was then generated using these models. The figure presented compares the real active shot gather data, which is the panel A, with the synthetic one, which is the panel B. The strong similarity between the two confirms the accuracy of the initial velocity model and supports its use as a reference for further analysis of the passive data. So let's now shift focus to how the passive ambient noise with data were processed. So passive data were processed by cross-correlating ambient noise recordings between receiver pairs to produce virtual shot gathers. Figure A shows the resulting cross-correlogram where casual and casual arrivals are observed symmetrically. The figure B displays a thin virtual gather clearly showing relay wave arrivals. A beamforming analysis revealed that most of the ambient noise energy came from the southeast, near a road and railway, which was ideal for the linear array orientation used in this study. So, with the virtual gathers prepared, the next step was to extract and interpret the dispersion information from the passive data. So, using the MHW technique, the researchers extracted dispersion curves from the passive data and inverted them into shear wave velocity profiles. The figure shown, panel A, represents CMP gather with relay wave arrivals. Panel B shows the frequency velocity spectrum and the extracted dispersion curve. Panel C to panel F, which is this, display the inversion results, including the 1D velocity model and fit quality. These models reveal the structures down to approximately 250 meters. However, due to the low frequency, long wavelength nature of passive data, resolution in the top 75 meters was limited. To fill in those shallow gaps, active source MSW was applied to provide more detail in the upper layers. The active source data provided higher frequency content, which allowed for greater resolution in the shallow subsurface, typically within the upper 75 meters. Applying MASW to this dataset revealed more detailed features, including a sediment layer approximately 20-meter thick overlying bedrock. These features were not visible in the passive data due to its limited frequency range. Overall, the active data filled a critical gap enabling high resolution imaging of near surface layers and completing the deeper information provided by the passive recordings. So the real strength of this approach came from combining both the data sets that we saw earlier. Uh, by merging the passive and active dispersion curves for each common midpoint, the researchers created a broadband dataset covering 6 to 50 Hz. This figure illustrates the expanded frequency coverage, while this figure shows the final 2D shear wave velocity model. So this combined profile revealed high velocity zones at the ends of the line, low velocity anomalies in the center, and several lateral contrasts that may correspond to fault zones or lithological boundaries. This mo- the model also showed strong agreement with passive-only results at depth. To better understand the strength and limitation of each method, let's take a moment to summarize their performance. So, for the summary of results, the slide summarizes the performance of each method. Passive seismic data allow deep imaging down to 250 meters but lacked shallow resolution. The active data provided high resolution images of the top 75 meters but did not reach deeper layers. But when combined, the two methods produce a continuous full depth velocity model with balanced resolution. Now let's discuss some of the challenges and considerations that arose during the study and how they were addressed. So for the discussion, linear arrays are often suboptimal for ambient noise studies due to directional bias. This site benefited from strong southeast directed ambient noise. The use of common midpoint stacking helped suppress incoherent signals and enhance data quality. So this figure compares the synthetic, the active, and the passive waveform data in the 6 to 16 Hz range, showing strong agreement and reinforcing the reliability of the passive method in this context. So let's wrap up with the key takeaways and overall significance of the study. So in conclusion, the study demonstrates that ambient noise surface wave imaging is a viable and effective tool for hard rock mineral exploration. When combined with active source seismic data, it offers a cost-efficient means to image faults, lithological contacts, and other subsurface features of interest. So this integrated approach has strong potential to reduce exploration costs and improve targeting accuracy in structurally complex geological settings. So thank you. That's it, and thank you for your attention. I hope you learned a lot from my discussion, and thank you again. Goodbye.